A Taylor series is an infinite power series, and here we have the Taylor series expansion centered on x equals a. And recall that the Taylor polynomial has this form, but it's finite, so the Taylor polynomial for the function f of x is the partial sum of the Taylor series for the function. So when we expand a few terms, the Taylor series looks something like this. And an example of a function that has derivatives of all orders at x equals a is the exponential function. And here we have the Taylor series expansion centered on x equals 1. So as we use more terms in the Taylor series, you get a better approximation to the function until you get the exact value if you use an infinite number of terms. And when the Taylor series expansion is centered on x equals 0, that's called the Maclaurin series. And in the coming examples, we'll see that the Maclaurin series for the special function 1 on 1 minus x is a geometric series, and the Maclaurin series for elementary functions gives the foundation for constructing the Maclaurin series for other functions, which we'll also show. Given a Taylor series expansion about x equals a, which can be written in this form, where f of x has derivatives of all orders at x equals a, we're asked to find a Taylor series of e to the x about a equals 1. So let's expand a few terms of this series. And given f of x is e to the x, well, all these derivatives are going to evaluate to e to the x. And evaluating these at x equals a equals 1, and then we can substitute these into this function. So as you can see, the more terms we use from the infinite series, we get a better and better approximation to the function e to the x about x equals a equals 1. So the approximation is better, close to this value, using less terms of the Taylor series. Let's show that the Maclaurin series for the following function is a geometric series. So remember the form of the Maclaurin series. So we differentiate the function a number of times. And evaluate the function and its derivatives at x equals 0. And you can see that these are factorials. And now we can write out our expansion of the function. So that will be f of 0 plus the derivatives on the factorials by x to the power of n. And you can see that the derivatives are factorials themselves, so these are all going to cancel. So this gives us a geometric series with a constant of 1 and a ratio of x. And therefore the geometric series converges with the absolute value of the ratio is less than 1. And this is the sum of the geometric series, as we've seen before. Find the Maclaurin series of sinx. Well, a Maclaurin series is simply a Taylor series expansion about a equals 0. So we can write the series as follows. And that can be expanded as follows using a few terms in the series. And f of x is sine x. And we differentiate this a bunch of times, up to the third derivative. And evaluating these at x equals a equals 0, and these derivatives just keep cycling. So now we can substitute back into the function, where f of 0 and f dash dash of 0 is 0. So if you keep cycling the derivatives, the next one's going to be x to the 5 on 5 factorial and so on. And now we can write this as an infinite series. So we have minus 1 to the power of n, which cycles through positives and negatives. And then when n equals 0, 1, 2, and 3, we have x to the power of 1, 3, and so on. So that will be 2n plus 1. And then divide this by 2n plus 1 factorial. Because we have 1 factorial for n equals 0, 3 factorial for n equals 1, and so on. And that's our series. Let's find a Taylor series of cosine x about x equals 0. So f of x is equal to cosine x, and we differentiate this several times. And evaluating these at x equals 0, we're basically obtaining the Maclaurin series. And now we can write our function as follows. So we have 1 minus 1 on 2 factorial by x squared. And then these derivatives will keep cycling. So our next term is going to be plus x to the 4 on 4 factorial. And then minus x to the 6 on 6 factorial, and so on. So therefore we can write our function as an infinite series. So we have minus 1 to the power of n to flip between positives and negatives. And for n equals 0, 1, and so on, we have x to the power of 0, x squared, and so on. So that will be x by 2n, as we can see. And that's divided by 2n factorial, because we have 0 factorial, 2 factorial, and so on. And that's our Maclaurin series for cosine x. Let's prove Euler's formula using the Maclaurin series for the following elementary trig functions. So if we start off with f of x and take the derivatives several times, and evaluate these at x equals 0, and now we can write out the Maclaurin series. So these derivatives will just keep cycling back and forth. So next we're going to get 1, and then I, and so on. And now we can group the real and imaginary terms together. And we've factored out the imaginary number. So as you can see, this here is cosine x, and this here is I sin x.